My name is Satvik Singh. I am doing a PhD with Nilanjana in Cambridge. But today I'm going to talk about some work that I did a couple of years ago before joining Cambridge. So this is work with Eon from Toulouse, and it's about these family of channels that we call diagonal unitary covariant channels. So these are just some class of finite dimensional channels which enjoy certain extra symmetries, which I'll talk about. And over the past couple of years, we have come to realize that this family of channels can serve as a nice testing ground for some conjectures that you might have or some calculations that you want to do on channels, because these are complicated enough to kind of inherit the underlying complexity that comes from entanglement and so on, but they are still kind of tractable. So that's kind of the main message of my talk. And keeping in view the title of not the title actually, since I'll only be talking about finite dimensions, so there's not going to be any infinite dimensional subtleties coming into picture. But today's topic is entanglement, so I'll mostly focus on the entanglement property of these channels. So to give you a quick introduction, you've seen from Andreas's talk that checking whether or not a given bipartite state is entangled is a hard problem. And in terms of channels, it means that it is very difficult to check if your channel breaks entanglement or not. And so the whole idea is maybe if we employ certain symmetries on our channels, then this problem becomes somewhat tractable. And this is exactly the case. And in particular, we will see that this diagonal symmetry will allow us to come up with a simple sufficient condition to check when a given channel breaks entanglement. And this in particular will allow us to show that the PPT squared conjecture that we got introduction about in the morning session by Warren, it actually holds for this general class of diagonally symmetric channels. So this is kind of going to be one of the main theorems of my talk. And then finally, I will try to establish like somewhat of a novel connection between certain kinds of graphs and the entanglement breaking property of these diagonally symmetric channels. I'll talk more about this towards the latter half of the talk. Okay, so for me, I'll only be talking about finite dimensions and complex matrices, no real here. So it's just going to be D cross D complex matrices. And state is just going to be a positive matrix for me, which is a unit trace, and a bipartite state, call it PPT. If you act on transpose on one part of the state, you get something which is still positive. And separable, we all know that if a state is separable, if it can be expanded, if it admits this kind of a convex decomposition in terms of product states. So let me just come to my main channel. So we will consider linear CPTP maps between these matrix algebras that are covariant with respect to the diagonal unitary group. So for all X and all U, this channel satisfies this covariance property. So now U is this du sub D is the set of all diagonal unitaries. So it's just diagonal matrices with just phases as its entries. And our channel enjoys this covariance property. And so it's not too hard to show this, but you can kind of completely parameterize these channels, the action of these channels in terms of two complex matrices, A and B. So the action kind of splits up into two parts. We have a diagonal action, which, and then we have like an off-diagonal action. And A and B are D cross D matrices. And if you impose the CPTP condition on this linear map, then it turns out that A must be a stochastic matrix, column stochastic, entry-wise non-negative. So this curly inequality just means that it is entry-wise non-negative. And this means that B is positive semi-definite, and the trace preserving condition imposes the stochastic condition on our matrix. And this here denotes the entry-wise product. So what this channel is doing, it's just taking the classical part of our state, the diagonal, and acting classically by a stochastic matrix. And then on the off diagonal, it's just acting entry-wise by this B matrix. It turns out that many interesting examples, which are like depolarizing channels, dephasing channels, amplitude damping channels, they are all special cases of this symmetry. So they all enjoy the symmetry. So in particular, if you require that your channel must be covariant under the full unitary group and not just the diagonal group, then you would retrieve the depolarizing family of channels, which would be just one parameter. But now here we have kind of d squared parameter. So you can think of these channels as lying somewhere between the kind of trivial depolarizing channels with just one parameter. And we have these channels somewhere in the middle, and then we have the full class of quantum channels.
So the diagonal entries of B don't play a role, right? So
yeah, so they have equal diagonals. So that's kind of like, so we just need diagonals of either of these two matrices, but yeah.
So you have D-independent phases, basically.
Yeah.
You have U1, many copies of independent U1.
So the symmetry should be
Symmetry group.
with respect to all unitaries. So we have D phases and yeah.
The diagonal unit.
Yeah, diagonal unitaries where the diagonal entries are the phases. Yes.
Do you have a similar characterization if you replace diagonals by two matrices of diagonals?
2 by 2 what do you
Block
diagonals?
diagonals in in half dimension, you can think of something like that, but yeah, quite like it.
Yeah, but no, I don't think we've, like, you can consider, I guess.
Also a notion of covariance, right? That's
Yeah, sure. Yeah, but I guess you can kind of come up with some kind of in each 2 cross 2 block, you will have some kind of structure, and then maybe the full thing would be like a direct sum of these individual blocks. I'm not sure, but we haven't looked into that. Yeah.
that would be a smaller collection, right?
yes.
Yeah,
No, it will be a
it
larger
would be a
connection.
bigger connection. Yeah, it would be a bigger group. Yeah.
Larger connection of
Yeah, this would be like a subclass of yeah. Okay, so the channel for me is going to be, we'll call it channel PPT if for all n and for all bipartite states, if you act only on just one part of the state, you get something which is PPT. And this is the same as so there are equivalent characterizations. This is the same as saying that the channel is completely positive and completely co-positive at the same time. So you've composed with transpose, you get something which is completely positive again. But I've phrased it in this way because it's kind of easier to relate it with the entanglement breaking property, which just means that now if you feed in any bipartite state, then and act on just one part of that state by our channel, then the resulting thing will have no entanglement, which will be it will be separable, and this should be true for all states. And so we saw a bunch of equivalent characterization of this property in Mohr-Stock, but for us, the characterization in terms of the Choi matrix is sufficient. So the channel is PPT if and only if Choi state is PPT, and similarly for entanglement breaking property, this is equivalent to the Choi state being separable. And so what we can now try to do is try to reformulate or rephrase these properties for our channels of interest. So this is easy to show that your phi AB, the diagonally symmetric channel, is going to be PPT if so these two conditions were already present, but now we have to satisfy some entry-wise inequalities between the entries of A and B. And similarly, we can reformulate the entanglement breaking property in terms of certain decomposition that the A and B matrices should satisfy. So it turns out that your channel will be entanglement breaking if and only if there exists a finite set of vectors such that A admits this decomposition and B admits that decomposition. So here the bar denotes entry-wise complex conjugation, and the dot we already saw it was entry-wise product. So just from the decomposition, it should be clear that this A is going to be entry-wise non-negative because these are going to be entry-wise non-negative vectors because of this conjugated product. And B is just a rank 1 decomposition, and so this is going to be positive semi-definite. And you can also check that the entry-wise inequalities are also satisfied because entanglement breaking property implies PPT property, but not the other way around. And so our idea is to maybe now checking if and I call a pair of matrices A and B, which satisfies this decomposition, which admits this decomposition to be pairwise completely positive. I will explain where this name comes from in a second. But the idea is now maybe checking membership in this new cone of pairwise completely positive matrices is slightly easier than checking membership in the cone of separable matrices. And that's kind of the whole point of this. But before going to that, let me just introduce a couple other terminology, some definitions. So this is a notion of factor width. So a positive matrix B, we say that it has factor width K if you can find a rank 1 decomposition for this matrix where each vector in the decomposition has just K non-zero entries at the most. So size of the support of each of these vectors is less than or equal to K. You can think of this as some kind of a coherence condition. So if you're just looking at factor width 1, you would just get diagonal matrices because the support of each of these vectors would just be 1. And as you get higher, you would have more and more coherence. So K equal to 1 would correspond to just diagonal matrices and so on. Similarly, for PCP pairs, we can formulate the factor width in this way. So now we are looking at the size of the common support of our vectors in the decomposition, Vn and Wn. And if this is less than or equal to K for all n, that we say that our matrix pair has factor width K. And so these sets are essentially like inner approximations to our cone of positive matrices. And so as you increase the factor width, you get closer and closer and closer to the positive semi-definite cone in the first case, and in the second case, the PCP cone. And as I mentioned, the factor width 1 set is just diagonal matrices. And for the PCP, the factor width 1 set is just going to be matrices where B is diagonal and A can be any entry-wise non-negative matrix. And so now we come to like the meat of the talk. So in general, it turns out that checking membership in the cone of PCP matrices is also hard, which is kind of a bummer because we were expecting it to be easier than the general problem. So you can show that if you replace B by A, then this pair A comma A is PCP if and only if A is what is called completely positive. And this is a separate notion than that of complete positivity of channels. This just means that A is positive semi-definite, and the decomposition of A in terms of this PSD decomposition, the Z must be entry-wise non-negative as well. So it's kind of combining two notions of positivity, of positive semi-definiteness and entry-wise non-negativity together to call what to arrive at complete positivity. And it is known, so this notion is well studied in combinatorics, and so people know that checking membership in the CP cone is also NP hard. So we have not actually gained anything. It just seems like we have reformulated our original problem in terms of an equally hard problem. However, it turns out that checking membership in the smaller approximation of factor width 2 PCP is easier. And we can formulate a nice characterization of this set in terms of what is called the comparison matrix. So for any D cross D complex matrix, the comparison matrix just is defined entry-wise like this. So the diagonal you just replace by the absolute value, and the off-diagonal elements you just take the absolute value and apply a minus sign. And now it turns out that if you have the diagonally symmetric channel, which is PPT, then it turns out that positivity of the comparison matrix is equivalent to the pair AB lying in the factor width 2 PCP cone, which is further equivalent to this just the B matrix having factor width 2 as a positive semi-definite matrix. So for us, the essential part is this. So we have like a simple condition, a simple sufficient condition, which can be easily verified and which implies that our channel in question is entanglement breaking. And this, it turns out that is exactly what we need to show that PPT squared conjecture holds for these channels. And so let me just quickly remind you of the conjecture again.
So
Yes.
A doesn't contribute at all.
Yeah, it's just the condition is entirely praised in terms of B, and in particular the comparison matrix of B. And the proof of this uses some elementary techniques from the theory of entry-wise non-negative matrices, the Perron-Frobenius theory. I'm not going to talk about the proof here, but yeah, we will use this simple condition to prove the PPT squared conjecture for these channels. So just to remind you of the conjecture, it just says that for any two PPT, I've formulated everything in terms of channels for this talk, but you can just replace it with, you don't need trace preservation. It just conjectures says that for any PPT linear maps, the composition must be entanglement breaking. And as was also mentioned in Wern's talk, that this is originally the motivation came from the study of repeaters. And so in terms of bipartite states, we can think about like this tripartite scenario. We have Alice, Bob, and Charlie, and Charlie shares some state with Alice, let's call it rho, and Charlie shares some other state, sigma, with Bob. And the task for the three parties is to apply local operations, communicate classically, do all local things. And then finally, we want to swap the entanglement that Charlie individually shares with Alice or with Bob between entanglement between Alice and Bob. And the conjecture basically says that if rho and sigma are PPT, then this task is futile because whatever you do locally, at the end, Alice and Bob must always share a separable state. So that was the original motivation for the conjecture, and we talked about the progress on the proof. So it is known to be true for d equal to 2 and d equal to 3. We also saw that if your channel is either unital or trace preserving, then it is asymptotically entanglement breaking. Then we also saw if it is unital and trace preserving, then finite iterations would give you entanglement breaking map. And now we know that it also holds for these diagonally covariant channels, which includes some interesting examples. Okay, and so the idea is basically just to use the comparison matrix criterion. And so we saw that if you have a PPT channel like this and B has a positive comparison matrix, then the resulting channel must be entanglement breaking. And how does this? So we just basically, the proof consists of taking two arbitrary PPT channels of this kind, which are parameterized by these four matrices A, B, C, and D. And the step one is to show that when you compose two channels which have the symmetry, then the resulting channel will also have the symmetry. And in particular, you can compute the matrices X and Y, which will parameterize the action of that channel. So X would just be the matrix product of A and C, and Y would just be the entry-wise product of B and D. And then you have to take care of the diagonal issues because the two matrices should have the same diagonal. And then it's trivial to see that PPT channels, when composed, the result is also PPT. So we are in the setting of our theorem, which is stated above. And so the only thing that we need to show is that this Y here has positive comparison matrix. And that is also not too difficult to show. And so once we show that M of Y is going to be positive, our previous theorem, so I messed up the numbering here. So the theorem above shows that the resulting channel is entanglement breaking. And that's kind of the proof. And yeah, so let me not discuss how you can show that the comparison matrix of Y is positive semi-definite, but the idea is you can just write down the expression. So this, I've just illustrated this for 3x3 case. And then it turns out that you can kind of decompose this matrix in terms of like 2x2 blocks. And for 2x2 blocks, we can use these entry-wise relations that we had, which came from the PPT condition, to show that they are entanglement breaking. So they are positive, not entanglement breaking. The matrix is positive. But yeah, let's just some technical steps that need to be taken care of. So yeah, that was the PPT squared conjecture for these diagonally symmetric channels. And in the second part of the talk, let me just mention the connection that I initially outlined between entanglement breaking channels and the graphs. So the idea now is just to kind of probe the converse of the result that we originally saw. So we saw that if we have a PPT DUC channel of this kind, then we have a complete characterization of the factor with two PCP matrices. And in particular, this means that the positivity of the comparison matrix implies entanglement breaking property of the channel. So what about the converse? So of course, the converse cannot be true because then we would have a if and only if characterization of entanglement breaking DUC maps, which is not true because we saw that checking membership in the PCP cone is NP hard too. But what we can try to do is kind of look for a subfamily of channels within this class for which maybe the converse also holds. And then we can have like an if and only if characterization for entanglement breaking property. And to do this, what I introduce what I call triangle free symmetric channels. So I'll just call phi sub AB triangle free if the associated graph G of A, which I define shortly like this, is triangle free. So what do I mean by this? So A is just a matrix. So let's say we are considering a 4x4 case, and I can associate a graph to this matrix and such that this matrix would be the adjacency matrix of this graph. So I just label these four vertices because we have a 4x4 matrix, and I join I and J vertex together if both Aij and Aji are non-zero. So in this case, we get this square graph, which doesn't have any triangles. So this would be a valid triangle-free channel. And so for these triangle-free channels, it turns out that if your channel is triangle-free, if your symmetric channel phi sub AB is triangle-free and entanglement breaking, then the converse of our result is true. So the comparison matrix must be positive semi-definite in this case. And the proof essentially just, so the crucial observation is, since the channel is entanglement breaking, we can think of a TCP decomposition of our matrix pair AB. And then we can use the triangle-free property of our graph to show that these vectors which lie in this decomposition must have small common support, because otherwise, if they had a support of size bigger than 3, common support of size bigger than 3, then the graph of the A matrix would contain a triangle. And so we can use the triangle-free property to ensure the support condition. And then this just basically means that since the supports are small, the matrices lie in the factor width 2 case, and the factor width 2 case was exactly the case which was defined by the positivity of the matrix comparison matrix condition. And so it turns out, so then we get this theorem that if our channel is triangle free and PPT, then we have like a complete characterization of the entanglement breaking property in terms of a simple matrix positivity condition. And what is this good for? So we can actually use this to construct new examples of states which are PPT but entangled, or channels which are PPT but not entanglement breaking. And we saw in the introductory session that these are interesting states because they are PPT, meaning they are bound entangled, so you cannot distill any entanglement from such states, but they are still entangled, so they have a positive entanglement cost. So, and right now, I think there are only a handful constructions of PPT entangled states based on certain other criterion, but this method gives us a new way to construct like a plethora of new examples of PPT entangled states, and which you can use to, for instance, you can, maybe these states have positive distillable key. And so these would be an interesting classes of states to do computations on. So the idea is just to start with the triangle-free graph, construct a matrix realization of the graph, by which I mean that construct a matrix whose graph is going to be the graph that we started with. And this matrix realization should be such that it is positive, but the comparison matrix is not positive. And then we can construct the corresponding A matrices, which would just have the same graph again as the graph that we started with, have the same diagonal as that of B, and we will satisfy these entry-wise conditions as well. So this, we are just making sure that the channels that we construct are PPT by these conditions. And then if this family of channels phi AB, where A comes from this family of matrices, would be a class of PPT channels which are not entanglement breaking because of the way that we constructed B. And so the only problem in this procedure is step 2, because it is not clear if every triangle-free graph admits such a matrix realization, which is positive semi-definite, but whose comparison matrix is not positive semi-definite. And this is a technical point, and you can take care of this. So so this is just a technical subtlety. It turns out that if your graph doesn't have any cycles in it, if it is acyclic, then positivity of B already ensures positivity of the comparison matrices. So these kinds of graphs will have to eliminate from our consideration. And so in particular, it would mean that if your channel phi sub AB is such that the graph of A is acyclic, meaning it doesn't have any cycles inside, then entanglement breaking property and PPT would just be the same thing. But if we have a triangle-free graph which does contain a cycle, so it must have like a square or a pentagon or some higher order cycle, then you can actually explicitly construct a matrix realization which is positive semi-definite, such that the comparison matrix is not positive semi-definite. And so some consequences, this just means that given any triangle-free cyclic graph on D vertices, you can associate a family of PPT channels which are not entanglement breaking, and these channels would be parameterized by around D squared real parameters. So just come up with whatever triangle-free graph you like, And with each of these graphs, this procedure would yield you a PPT family of channels, which is not entanglement breaking. And so since so you can like come up with whatever wild graph comes to your imagination. And since the number of triangle-free graphs on D vertices increases dramatically with the number of vertices, so it means that so does our families of new PPT entangled states or PPT not entanglement breaking channels. So for instance, in a 15 tensor 15 system, this procedure will yield you 10 to the power 10 new PPT families of channels which are not entanglement breaking. Yes, so that was kind of
Which unfortunately all fail the PPT script.
yeah, for like let's hope so. Yeah, so if we want to find a counterexample to the PPT squared conjecture, you must start with something PPT which is not entanglement breaking. So these 10 to the power 10 families can be your potential counterexamples. But yeah.
And you've shown that they satisfy.
Yes, okay, yeah. Not these ones, but you can kind of so let me just come to the future direction for so you can kind of so the PPT squared conjecture is open in general now, but in particular, it's still open for this trivial generalization that we can think of. So instead of now taking just diagonal unitaries, let's just take diagonal sign matrices, just plus minus 1 on the diagonals, diagonal orthogonal matrices. And this trivially generalizes our channels because we are now imposing less covariance condition, less number of conditions on our channels. So it turns out for these channels, you'll get an extra matrix that parameterizes the action. The action will again be of a diagonal kind and an off-diagonal kind, but now we have an extra matrix C that we need to take care of. And you can repeat the entire analysis and you can show that this channel is now going to be entanglement breaking if and only if this triple Y is completely positive and so on. But then now crucially, the comparison matrix condition, the criterion that we had for showing entanglement breaking property fails. And that is why we don't know if the conjecture is true for these channels. And I did not mention this, but this triangle free, this construction actually works to construct channels of this kind, which are PPT, but not entanglement breaking. So maybe some of these channels can be potential counterexamples. But I haven't checked every 10 to the power 10 family, like for obvious reasons, but yeah. And then finally, explore further connections. So what's special about triangle free? Maybe you can come up with the same criterion for like square free graphs or pentagon free graphs or n cycle free graphs to come up with new classes of PPT entangled states. What about, so these states that we construct are PPT means that they are undistillable when you talk about entanglement distillation, but what about the private key? Maybe they have some amount of key in it. What the questions of that kind and so on. So I guess I finished a little early. Thank you so much for your attention.